I want to tell you about the Königsberg bridges problem, which has a lot of interesting math behind it and also has some interesting mathematical history involved. Um, so the story goes like this. In Königsberg, which is modern day Kaliningrad, um, there is a river, the River Pregel, which has these two branches here, and there's also a big island in the middle of the river. So this is in the middle of the city. And there were a bunch of bridges, which I have drawn with these little arcs here, that cross the river in various places. And the story goes that people posed the following problem. Is it possible to go for a stroll and cross all 7 bridges without going over the same bridge twice and then coming back where you started? So you could try. You could say, well, let's start here and we'll go, if we go like across this one, and then maybe we'll go this way, and we can go up here. Oh, but now we're stuck, right? Because I can't go over these bridges again. I didn't get this one. So, but that doesn't mean there's not a way to do it. Maybe I just picked the wrong way. And so, people wondered about this, whether it was possible. And no one had found a way to do it, but no one kind of knew how to argue that it definitely wasn't possible. Maybe just no one had been clever enough to find the right way to do it. So Leonhard Euler, who was one of the most prolific mathematicians ever, so he came along and he said, that's a cute problem. And in 1736, he published a paper that completely solved the problem. And not only did he completely solve the problem, but he basically invented graph theory to do it. And so in some sense, this is like the birth of what we're studying now, graph theory. Because Euler's great insight was, like the fact that there's an island and there's like these rivers and stuff and they're in particular physical locations, none of that matters. Really what matters is that we've got certain pieces of land that are connected by bridges. And so he said, well, let's just label the pieces of land by by letters. So we call this A, and this B, and this C, and this D, right? We can abstract from the physical geography and just say, well, I've got A, B, C, D, and I'm going to draw an edge in between 2 of these whenever there's a bridge connecting them. So, A is connected to B twice, B is connected to C twice, C is connected to D, A is connected to D, and then finally B is connected to D. Okay? And so he transformed the problem from this physical manifestation into this abstract graph version. And so the question is there a path in the graph that goes over every edge exactly once and then comes back to where it started? So a cycle in the graph. In general, for a graph, we can say an Euler circuit, right, or an Euler cycle. Sometimes you'll hear people say Eulerian instead of just Euler. There's a lot of variants, but so it is a simple path, a simple cycle. I'll say what simple means in just a minute. Containing every edge of G. Okay? And an Euler path Euler path is similar, it just doesn't have to be a cycle. That is, it doesn't have to come back to where it started. So you could start at one place and end in another place as long as you go over every edge exactly once. Okay. And so the question is, when does a graph have an Euler circuit or an Euler path? Okay? And one thing to notice, and this was Euler's insight on this problem in particular, is that every time, if we have a path, right? Here's the path, it's coming along, it's going this way, and it goes through this vertex, and then it keeps going this way. When it comes into this vertex and then goes back out, since I'm not allowed to reuse edges, right, it basically uses up these edges, and it uses up exactly 2 edges. So every time that we go through a vertex, we use up 2 edges. And so let's think about Euler's circuits in particular, right? If there was a vertex that had an odd degree, right, then any kind of Euler circuit would have to go through that vertex some number of times. But every time it goes through, it uses up 2 edges. And so I'm going to be left at the end, once I go through it some number of times, with like only one vertex or one edge that's not been used. And now I'm stuck. I can never, if I ever go there, I'll get stuck at that vertex, and I won't be able to go back to where I started. Right, and even the starting point, this is true, is I'll leave along one edge, but eventually I have to come back along another one. That uses up 2 edges. And I might go through it some other number of times, but I'm going to use up 2 edges every time. So a path uses 2 edges every time it goes through a vertex. Okay, so that means in a theorem, if a graph has an Euler cycle, that means, right, every vertex has to have an even degree. Because if any vertex had an odd degree, then I would eventually be left with only one edge that's not used if I tried to make a cycle, and I would get stuck there. I wouldn't be able to get back out. Okay, so then every vertex has even degree. Okay, and so Euler was able to solve this problem by saying, well, look, this vertex, like actually all the vertices have an odd degree. So this is degree 3, degree 3, degree 3, and degree 5. And so the contrapositive of this theorem says, right, if a graph has any odd degree vertices, then it cannot have an Euler cycle. And so Euler was able to prove that, in fact, there's no possible way to solve this problem. And we could look at a couple more examples. So oops. So let's look at this graph. This is the bow tie graph. All these vertices have degree 2, 2, 2, 2. This has degree 4. So, and in fact, it does have an Eulerian cycle, right? So if I go like this way, right, that is an Euler. I visit every edge once, go back to where I started. Okay. So great. If I, here's another. So here, yeah, see, this is no good. We've got all these vertices have degree. This vertex has degree 4, but these ones on the outside have degree 3. So the theorem tells us that it can't possibly have an Euler cycle. What if we do something really crazy? So I made one here. So I'm making a graph that is complicated, but I've made it carefully so that every vertex has an even degree. And you can double check. But okay. I'll let you double check, but I claim every vertex in this graph has an even degree, right? So 2, 4, 1, 2, 3, 4, 5, 6, 4, 2, 2, 4. Yeah, so if I've done it correctly, everything has an even degree. So, and this is actually an interesting question. So this theorem just says if a graph has an Euler cycle, then it has an even degree. Every vertex has an even degree. So this theorem actually doesn't tell us, right? This the theorem really doesn't say anything, right? So we can't say for sure it doesn't have one. But does it have one? I don't know. The theorem actually doesn't tell us. And so this actually is all Euler proved. He didn't show like the converse or say anything about the converse. So in the next video, we'll consider whether, like, is this an if and only if, for example? Might there be some graphs where every vertex has even degree, but there is not an Euler cycle? But on the other hand, if there always is, like, how would we find one? So we'll talk about that in the next video.